All right, so this is the notes for the first of only 2 lessons we cover in Chapter 9. And Chapter 9 explores what we call rational functions, which connects to a small part of Pre-Calculus 11 you may or may not have really learned about, depending on what your focus was for that course. In general, a rational function, though, is any function that can be written like this, where you have f of x and g of x, but they're both polynomials. And hey, we just finished a unit on polynomials. So any function that can be expressed like this, as one polynomial divided by another, is an example of a rational function. There is a huge variety of types of functions you can have. Because there's a huge variety of polynomials and divide them in different ways, there's a huge variety of things. These functions often have discontinuities, which is where the graph breaks apart in some way. There's 2 types of discontinuities we're going to look at. An asymptote is one example of a discontinuity. We'll look at 2. Okay, but in general, a rational function is anything like this. Some polynomial divided by another. So a huge variety of options. That's it. Let's look at one of the simplest possible rational functions, just 1 over x. 1 is a polynomial, very simple one. X is a very simple polynomial. So 1 over x is what we call a rational function. And that's what's graphed right here. So some details of 1 over x I'd like us to be aware of. First of all, 1 over x goes through 1 comma 1 and negative 1 comma negative 1. 1 over x also has asymptotes. It has a horizontal asymptote right on the x-axis. And it has a vertical asymptote right on the x-axis. So let me make sure we're really clear what an asymptote is. An asymptote is not part of the graph. An asymptote is a symbol that describes the behavior of the graph. And for example, let's look at the vertical asymptote. That's because you can't divide by 0. But that's part of it. Division by 0 makes no sense. 1 divided by 0 means taking 1 and breaking it up into groups of no size at all. That's not possible. Hence, my graph doesn't exist when x is 0, because my input is x, my output is y. 1 divided by 0 is not defined. However, more important than just that is that you can't divide by 0, but you can divide by numbers really close to 0. And the closer you get to 0, kind of weird things happen. And so let me switch to a calculator here. And so notice 1 divided by 0, this says undefined. Different calculators say different things. Okay, I can't do that. But what about a number close to 0, like 0.01? It equals 100. And that's because if you took 1 and broke it up into groups that are each just 0.01 in size, you would have 100 groups, which makes sense. 0.01 is quite small. But what if I divide by a number even closer to 0? What about that? Notice 1 divided by 0.000001 is 10 million. Well, you kind of get the idea that there's no limit to how close I can get to 0. I can't divide by 0, but I can get really, 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 really close. And when I do, my numbers keep getting bigger and bigger and bigger. This is 1 times 10 to the power of 26, which is 1 followed by 26 zeros. And so you can't divide by 0, but as you divide by numbers really close to 0, and the closer you get to 0, the larger the outputs get. And there's no limit to how there's no limit to how close I can get to 0. There's no limit to how many zeros I can put here. Oops, I should put a decimal point first. But it's kind of silly for me wasting my time doing this more and more, because I just know the more I add before I hit a 1, the bigger my output will be. So the same thing if it's negative. If I go 1 divided by a negative 0.00001, I get really large negative numbers. And everything I just showed there is visually described in this graph. Notice when we approach 0 from the right, my outputs keep getting larger and larger, infinitely so, as we get closer. And if I approach from the left, which are negative values, my outputs keep getting smaller and smaller in terms of closer to negative infinity. And the asymptote shows us this break. The asymptote shows us that not only does the graph never reach 0 on the x, but it gets infinitely close to it on either side and goes infinitely up or infinitely down in this way. Same thing on the x-axis. It never actually reaches 0 because you can never have an output of 0. You can never go 1 divided by a number and get out 0. And that's because you can't take 1 divided by some number and get nothing at all. You can get close to 0, but you can't get nothing at all. And so all those things describe 1 over x. So that said, if you look at the graph of 2 over x, one way of thinking about this is 2 times the graph of 1 over x. If I think about it like that, then I realize that 2 over x is going to be the exact same as 1 over x, except vertically expanded by a scale factor of 2, which means I can kind of visualize what 2 over x would look like. Those 2 points I drew before are now going to be 2 times farther away from the y-axis. Or I can imagine this actually being expanded horizontally by a scale factor of 2. In the end, that would be the same thing. And so I get something that looks like this. And so this here is my sketch of 2 to the power of x. Sorry, 2 to the power of x, 2 over x. And once you realize that nice sort of symmetry here, then adding a 4 here is not a big deal, especially if I think of it as 4 times 1 over x. I can go back to my 1 over x and multiply all my outputs by 4. And so starting with this point up here and this point down here. But as well, you know, again, there's a bunch of ways of looking at this. But for example, if I look at this point right here, I just drew in red. That's when x is 4. When x is 4, I know 1 over x is 1 over 4. Right, it's 1 over x. Well, if I take that and times by 4, I have just 1. And we start to notice how all these graphs are symmetrical around these 2 quadrants. So once I know those 2 points there, I also can draw these 2 points I'm highlighting in green over here. And so suddenly, quickly, I have 4 points drawn. And what I just did to find this point right here, I can do at any point. For example, let's look when x is 2 on 1 over x. Well, when x is 2 on 1 over x, that's 1 over 2. Times that by 4, and I have 2. So I have a point right here. And notice all these graphs are symmetrical to one another. And now I got more than enough to draw what 4 over x looks like. And the point is that all these variations of 1 over x, I'm not saying they're simple, but there's tons of symmetry. Once you know one point, you tend to know a whole bunch of other points. There's my graph of 4 over x. And lastly, 6 over x. I'll do pretty quickly. So I can see it's going to go through 1 comma 6. It's also, maybe we can guess it's going to go through 6 comma 1. And if I know those 2 points, I know I can also draw 2 points over here. And then I can just, if I just keep plotting more points like I did before, just picking some points on 1 over x, or even just picking some points here. Replace x with 2. 6 divided by 2 is 3. And notice that's what I plotted when x is 2, y is 3. That's what I plotted right there. And once I know that point, I kind of know this point right here, because there's all this symmetry. I know I'm doing this pretty quick, but you can pause this and you can double check some calculations. And so if I look at this, well, I can start to see that compared to 1 over x, as I change that 1 to a 2, a 3, a 4, a 5, a 6, I have the same sort of shape. It's just kind of expanding, in a sense, away from 0, 0. But it still has these asymptotes. It's still the general, same sort of general shape. And if you graph these in Desmos, you'll see they all behave in the same sort of way. With that said, before I go on, let me just mention one other point. Let's say this point right here. Okay, if you're not sure where I got that, well, that's where x is 3. And again, literally, go back to this equation, replace x with 3. 6 divided by 3 is 2, and that's where that point is. And once I know that point, I can see it's going to kind of connect back to this point here. And there's all this symmetry between these shapes. All right, with that said, let me clean this up a bit and move on. Oh, domain and range. Don't move on quite yet. The domain of this function is any number that's not 0. And so the best way of saying, I think the best way of saying that is just say x cannot equal 0. Okay, that implies x can be any other real number. The range is the same sort of thing. Y cannot be 0, which we can kind of see from our asymptotes. Our asymptotes show us these breaks in the graph. And if I was to describe where these asymptotes are, the vertical asymptote we could say is where x equals 0. The horizontal asymptote is where y equals 0. In this case, that's also the same as I could say the x and the y axes. All right, so let's transform these a bit. So let's look at this. And let's think about what minus 4 over x plus 3 looks like compared to 1 over x. So what can I see here? I can see that I want to start with maybe 4 over x, which I graphed right here in green. And 4 over x I can think of as a transformation of 1 over x. So let me graph 4 over x first, and I'll show that kind of lightly in green here. So 4 over x goes through 1 comma 4 and 4 comma 1. And therefore, it goes through -1 comma -4 and -4 comma -1. As well, again, I'm thinking about what 4 over x looks like. If I replace x with 2, and I just pick 2 because it's a nice number, 4 divided by 2 is 2. So when x is 2, y is 2, which means I also have this point here. So I have really quickly sketched 4 over x. I really just copied the work I had from the last page. OK, so there is 4 over x. OK, so compared to that, what else do I see? Well, 4 over x is being multiplied by -1, or a negative in the front. That is a vertical reflection. So in a moment, I'm going to take this and I'm going to reflect it vertically. I also see right here, the whole thing is having 3 added to it, so that's up 3. And so I want to move this up 3. So at this point, I want to basically apply those transformations to what I sketched. The first thing I would actually recommend, now that I know I'm going to take this shape and reflect it and move it up 3, is I would actually recommend drawing my asymptotes first, because my asymptotes kind of give me a bit of structure. Plus, my asymptotes are something that are fairly unique from what we've learned so far to this group of functions. And so 4 over x has an asymptote right on the y-axis. If I move it up 3 and reflect it, that won't change. So my final answer is still going to have a vertical asymptote right on the y-axis. I'll leave that there. But because eventually, compared to 4 over x, my graph is going to move up 3, my horizontal asymptote I know is going to be right here. So I'm going to draw that right now as sort of a structure to work around. And so I know not to cross that. I know at some point my graph's going to get infinitely close to these places. And so now if I kind of take what I have in red and flip it over and move it up 3, I should get points right here. And so I'll kind of show just my final answer here. So what I have here drawn in blue is the graph I started with in green, reflected vertically and shifted up 3 units. Now I did that fairly quick, mainly because we've done these sort of transformations a lot. That said, the more we kind of have an internalized view of what 4 over x looks like, and we know these transformations, we can actually get to this quite quickly. Keep in mind, I sketched 6 points in detail for my graph, as well as the asymptotes. So there's a lot of detail to this graph. And the key was coming back to various transformations, which also is where all of this started with. All right, let's try this one. What transformations do I see here? I can see, first of all, this is sort of a transformed version of 2 over x, which I'm not going to draw this time because I have it already drawn at the beginning of our notes. Okay, but compared to 2 over x, I can see this is, I'm having 3 subtracted from the x, so that is right 3. So compared to 2 over x, I want to move it 3 right, and I want to move it 1 down. And all that's compared to 2 over x. So this time, just for something different, I'm going to actually start with my asymptotes. Because if I'm taking 2 over x and I'm moving it 1 down and 3 to the right, I know I must have an asymptote, a horizontal asymptote at y equals -1. Because I moved it 1 down. And if I'm going to move 2 over x 3 to the right, I know there must be a vertical asymptote right here. If I draw that right away, which is really, I'm just paying attention to my translations, which is some of the easier transformations to pay attention to, then I can visualize the sort of structure I'm going to work around. Other than that, the only other thing I need to think about is this is not 1 over x, it's 2 over x. So I could go back to the beginning of the notes and take that image that we sketched out for 2 over x and move it 3 to the right and 1 down. Or I can do this. I can think about what if there was a 1 right here? What if this was, I was thinking about 1 over x, or maybe I'll show it like this. What if my actual question had just a 1 over x minus 3? If there was no stretch, then it would go through this point here and this point here. It's literally the same thing I started with that was actually drawn in your notes. maybe I'll just make this actually a dashed line. It would look something like this. So again, this is me essentially simplifying the question slightly, which is a great logical idea for any problem, as long as we don't forget at some point to unsimplify it. So what I have there drawn in red, that is the graph of y equals 1 over x minus 3, take away 1. Literally the graph of 1 over x, that's in your notes, printed off, move 3 to the right and 1 down. The only difference compared to that is it's not a 1, it's a 2. And so those points are going to be, instead of where I drew them, they're going to be right here and right here, or right, everything's kind of symmetrical. And I have this, which again is identical to the graph of 2 over x, which is sketched out in the beginning of the lesson, but moved 3 to the right and 1 down. By the way, for this one, the domain, we would say is 0 is OK, but x cannot equal 3. If you look at my, for example, just by looking at the equation, when x is 3, I'm dividing by 0, or looking at my graph, I have a vertical asymptote at 3. And my range, 0 is OK, y can be anything but -1, which I can see on where my horizontal asymptote is there. All right, so let me talk about another type of discontinuity. OK, so an asymptote, which again you may have learned about in grade 11 or not. An asymptote is, I've already described, it's a line with which the function gets infinitely close to without actually crossing. And they're usually shown with dashed lines. OK, I've already mentioned that. A point of discontinuity is a bit trickier. It's an infinitely small point with which a function gets infinitely close to without actually crossing. They're usually shown with an open point. So it's an infinitely small hole, which is kind of a weird idea because that's small. It's infinitely small. So I'll get to that in a bit. So for each of these graphs, what I have for all these equations, f, g, and h, what you see is the graph that Desmos has created. So when you look at f here, I typed in 4x minus 5 over x minus 2, and that's what you see here. OK? I want to show the discontinuities on the graph. And so, for example, looking right here, I can tell there must be a vertical asymptote when x equals 2, because when x equals 2, I'm dividing by 0. So I'm going to show a vertical line, a vertical asymptote, where x equals 2. And notice it kind of creates this nice divide in my graph where my curves kind of break apart. However, there's also a horizontal asymptote, and it's hard to tell immediately where it is. But I can see it must be right here, because all these graphs are symmetrical. And if I draw it anywhere else, these two graphs won't be kind of symmetrical from each other around this. And so there is a horizontal asymptote. We say there's a horizontal asymptote at, in this case, where y equals 4. And there is a vertical asymptote at x equals 2. Now notice the vertical asymptote, I could kind of get an idea just by looking at the equation right here. When x equals 2, I'm dividing by 0. The horizontal asymptote of 4 seems kind of random. Yeah, there's a 4 up there, but that's not so simple. I figured that out, remember, by looking at the graph. OK? And I will say, without just looking at a graph, sometimes finding a horizontal asymptote, depending on the rational function, requires some work in calculus. Sometimes it requires some stuff we will look at in this lesson. So you will notice, in general, we're going to focus more on vertical asymptotes than horizontal asymptotes. Although in this particular question, I gave you the graph, so you can visualize it. You're just kind of drawing on it. But you will find we're definitely going to focus on vertical asymptotes generally more often, because finding them is a bit simpler. OK, let's look at the next one. This is the graph of 1 over x plus 4 all squared. So again, just by looking at my equation, I can see if x is -4, I'm dividing by 0. And if I look at my graph, I can see there's a break at -4 on the x. So there's my vertical asymptote. The horizontal asymptote is a lot more tricky by looking at the equation. In fact, just by looking at the equation, it kind of goes beyond the scope of this course. But I have a graph here. I can kind of see the horizontal asymptote. It's right on the x-axis. So to label this algebraically, the vertical asymptote is at where x equals -4. My horizontal asymptote is at where y equals 0. Those are where my two asymptotes are. And again, for each of these questions, I'm just asking us to label the discontinuities, draw them on there. Which leads me to perhaps the weirdest one. Okay, h of x is 2x squared minus 7x plus 5 all over x minus 1. Okay, this is the graph of what we get. It's a straight line, which may seem kind of surprising at first. And if you graph this in Desmos and you zoomed out, it just keeps looking like a linear function. So first, why is that? Well, let's look at the equation. And if I factor my numerator, we can see why it behaves like a line. If I factor my numerator, it takes a couple of steps. We should eventually get 2x minus 5 as one factor and x minus 1 as the other. So all divided by x minus 1. If I write my numerator in factored form, I can cancel these out. Now what I just did is part of Pre-Calculus 11. Pre-Calculus 11, we deal with rational expressions, and we deal with rational equations, and we simplify them, we solve them. You don't graph them. That's the main difference here. We're graphing these. But what I just did right now, taking 2x squared minus 7x plus 5 and using the factors of it to simplify the expression, is something you've done before. Well, you should have. Which means that fairly messy expression simplifies down to just 2x minus 5. And that's what we see right here. This line, notice, has a slope of 2 and a y-intercept of negative 5. Okay, but it's not 2x minus 5. It's 2x squared minus 7x plus 5 divided by x minus 1. And you may remember as well, when you did work like this in Pre-Calculus 11, we talked about restrictions. And the restrictions are numbers that x cannot be. And for example, if I look right here, or if I look right here, x cannot equal 1. If x equals 1, I'm dividing by 0. And once I cancel out these factors right here, it's easy to miss that. But again, this is what I'm trying to focus on the graph of. This is a simplified form of it. And so it definitely simplifies down to 2x minus 5. But still, x cannot equal 1. If x equals 1, I'm dividing by 0. So I need to include that right here. X cannot equal 1. So on the graph, that means h of x looks just like the line of 2x minus 5, except x cannot equal 1. So that means when x is 1, not 1.01, that's okay, not 0.99999, but when x equals 1, my graph does not exist. My function does not exist just at 1. So how do I show that? Well, here's where x equals 1, right here, and I kind of make my way down, and I have to make an open point there. So I'm going to grab a little white pen here, and I have to adjust my graph. Ooh, I just changed my color. There we go. And I need to erase what's inside there and make it just an open point. So that there is what we call a point of discontinuity. It's an infinitely small hole, but it's still a break in my graph, an infinitely small break, which is kind of a weird idea. Point of discontinuity. And I said there's two types of discontinuities we look at in this chapter. Vertical asymptotes and horizontal asymptotes. Asymptotes in general is one type. Points of discontinuity is the other. And they're kind of weird. They're infinitely small holes, but you know, if I just look at my function h, if I replace x with 0, I'm dividing by 0, and it does not matter the context. Division by 0 does not make sense. And so I have this infinitely small hole, and which, you know, is pretty small. Okay, so my last problem, again, is kind of like some algebraic work that is in some ways familiar to what you would have done in Pre-Calc 11, but backwards. All right, so first of all, what I have here, if you look at this equation here, and you look at this equation here, they are equivalent. They are written differently, but they are equivalent, which means if I were to graph them, they look exactly the same. And if I look at this form, I can see the transformations. For example, if I look at this, I can see that this is the graph. I can visualize this as the graph of 3 over x, moved 2 to the right, and then moved up 4. I can visualize that. And as long as I know what 3 over x looks like and these transformations, I can quickly have a visual. If I look at this, I can't see much, but these are equivalent. So how can I prove that they are the same? Okay, that's the first thing I do here. So what I do here is first show, if I look at this step right here, algebraically, I'm taking this and I'm showing you how it's the same as what you see over there. And essentially, I'm finding a common denominator. So again, let's focus on this. And this, again, is straight out of Pre-Calculus 11, which is working with rational expressions. So if I want to put this all together into a single fraction, because that's what I really have right here. I have a single fraction. I need to find a common denominator. And to find a common denominator, I make that 4 look like 4 over 1. And I multiply the numerator and the denominator by my lowest common denominator, which leads me to this step right here. Once I have a lowest common denominator of x minus 4, I can put them together into one fraction, which is what I have right for this next step. And so notice up here I had 3 plus 4 times x minus 2. That's what I have here. 3 plus 4 times x minus 2, just written as a single fraction. Then I distribute the 4, which leads me to this. Then I collect these two like terms, 3 negative 8 or negative 5, and voila. What we have here, I've now proved is the same thing here. Okay, so all I've done so far is prove to you that I wasn't lying, that these two equations are equivalent. But how can you go backwards from here to here? And that's not something you would have done before, and that's what I'm doing right here. All right, so I'm going to work through the steps here, and then I encourage you the final problem is really trying it somewhat on your own. It's kind of a weird idea. It's essentially all these steps in reverse. So let's look at these steps backwards. If I want to go from here to here, notice what I have to do. At some point, I have to break this up into two fractions, each with the same denominator. But then there'll be a common factor that will cancel out, leading me with this constant. Okay, so my goal to go backwards is to take this expression at the bottom now and eventually break it up into two fractions, one of which will have a common factor, in this case of x minus 2, that'll cancel out, leaving me with my constant term. So how can I do that? Well, let's look here. What first thing I do is I essentially give myself some space. Okay, then notice right in this space, I put minus 8 plus 8. Why do I do that? Well, first of all, minus 8 plus 8 is 0. So while I've changed the way the expression looks, I haven't changed what it means. It's still, I essentially added 0 to the numerator. But if I do that, I can now factor a 4 out of these two terms and get x minus 2. Why is that useful? Because I eventually want to cancel out that x minus 2. So once I subtract 8 and add 8, I can create that factor of x minus 2 in my numerator. Plus I have some plus 8 minus 5, some constant of positive 3 over there that I don't really care about. Now I can break it up into two separate fractions, each with the same denominator. And at this point, I can now cancel out that factor of x minus 2, which leads me to this, which is the exact same thing we had in the other expression, just written in a different order. Okay, it's definitely way harder, I think, than what I did right here. But it's the same idea, but everything's in reverse. Okay, so that's with me having everything already done for you. So now your goal is to try it with this. And as always with questions like this, I would highly encourage you just to pause the video in a moment, try as much as you can on your own, and then I'll show you how we can approach it. Okay? In the end, though, you want to try to put it into, you want to take this equation like this and put it into this form. And if you've done so properly, you should be able to see all the transformations and visualize the graph. Okay, I recommend to pause the video. I'll work this out in just a moment. All right, so what would I do first? Well, first thing I want to do, and it's definitely optional, but I want to put my negative 2x term first. In my numerator, I want to put positive 10 second and give myself some space. And this x minus 3 I see down here, at some point I need to create a factor of x minus 3 in the numerator so that it cancels out. So I have a few ways I can do it. One thing I could do is I could just put minus 3 here. Okay. However, if I'm going to do that, I need to put brackets around this. Okay, because I want x minus 3, not 2x minus 3. However, if I do that, I have to balance out my expression in some way. So I just put a minus 3 here. So I have to do the opposite of that. But it's not, this is not minus 3. This is minus 3 times negative 2, which is positive 6. So really, when I put put that minus 3 in the brackets right there, I actually added 6 to my numerator. So to balance it out, I need to subtract 6. Now, this is the exact same idea as what we do with completing the square. But now I have everything set up. I have the hardest part done, in my opinion. I have found a way to create this factor of x minus 3. And so let's clean this up a little bit. Let me write this as negative 2 times x minus 3 plus 4 all over x minus 3. Okay? Or I can maybe even skip that step and get straight now to having two separate fractions. Minus 2 times x minus 3 all over x minus 3 plus 4 over x minus 3. At this point, I hope it's pretty clear that these x minus 3's cancel out. And so I have my constant term of negative 2 plus 4 over x minus 3. And I'm done. Usually we put the 4 over x minus 3 first, minus 2. So I can now see that this function here that I started with, if I zoom out a bit, 10 minus 2x over x minus 3, I know can be written like this, which means I can now start to visualize what this function looks like. This function up there is going to look like the graph of 4 over x, which itself is going to look like the graph of 1 over x, but expanded vertically by a scale factor of 4. So it's going to look at the graph of 4 over x, move 3 to the right, and 2 down. A lot of things we covered here. Notice how the transformations keep coming back. And chances are these last sort of questions are some of the hardest ones to look at. But I've talked for a long time. My throat's getting dry. You're probably sick of my voice. Let's end this.